I'll get started then. So I'm going to show you the proof of the, u-substitution. So here's the theorem. This is on page 237 of my notes, which means there's more examples we'll come back to. I just wanted to get this theorem out of the way. So this is on change of variables. And so here's the preconditions. Suppose G is continuous on the closed interval from A to B. With, well, my theorem in the notes is a little bit more. I'm just going to state it like this: with f is differentiable on the on AB open. I think I've got a typo in the notes right there. Then number one, the integral of g of u du evaluated at u equals f of x is equal to the integral of g of f of x df dx. And number two, the integral from f of a to f of b g of u du is equal to the integral from a to b of g of f of x df dx dx. So if you just kind of take a step back and stare at this for a second, you'll see it's what we were doing last class. Like basically we were starting with the right-hand side of the above expression, and we're canceling the dx out, so to speak, right? And so like the substitution here is u equals f of x, right? That I've not written yet, and I should. I'll get that out of your way. And so here the substitution in play is, again, like I said, u equals f of x. And apparently, having written what I've written, we assume what? df dx exists, right? On, closed interval from A to B, I suppose, something like that. Now, my claim is that, what does it mean to claim number one? Let me go through the proof for us, all right? Since G continuous on AB, the integral of G of u du is equal to big G of u, right? Where G prime of u is equal to G of u, right? How do I know that? This is the fundamental theorem of calculus, part one. It says that an antiderivative exists for a continuous function, right? So I know an antiderivative, big G, exists for that. Okay, so let's see here. So let me try to calculate d dx of the integral of g of u du evaluated at u equals f of x. So what is that? Remember that the integral of g of u of du is big G of u, right? So this is big G of u evaluated at u equals f of x, right? So that's d dx of g of f of x. But what's that? Well, by the chain rule, this is g prime of f of x times df dx, right? But what's g prime equal to? Remember, g prime, big G prime is little g. So this is literally little g of f of x df dx. But on the other hand, this is equal to the derivative of the integral of g of f of x df dx, right? Because the derivative of any integral, indefinite integral, the derivative of any indefinite integral is just the integrand being integrated, right? So what I've shown now is that the derivative, I have shown that the derivative of the left-hand side is equal to the derivative of the right-hand side, and that's what justifies this equality. This is an equality of indefinite integrals, which means that they have to match to a derivative, right? We agree that writing this kind of equality, we agree that one could be the other plus a constant or something, right? That's in the water here when we're talking about indefinite integrals. So that's one. It's really just the chain rule. But as you can see, like I told you guys before I started the video, this is a proof that I have to look up in my notes. To me, it doesn't come naturally. There's something backwards about all this. In contrast, the examples we did last class are a piece of cake. I mean, for me, I know you guys are still learning, but those were pretty straightforward. I mean, once you get going and you understand how the notation works, it's not hard. But this is the theorem that underlies that notation, all right? And how do you prove 2? Well, to prove 2, notice that, so the integral from a to b of g of f of x df dx, well, an antiderivative for that is what? It is big G of f of x. I mean, that's what this is, right? The left-hand side is big G of f of x. So that's an antiderivative for this by 1. And I can evaluate it from a to b, which gives me G of f of b minus G of f of a, which, of course, in turn, is what you get from the integral from f of a to f of b of little g of u du. So 1 naturally leads to 2. But let me, so I mean, I've never asked the proof of this on a test because it's an unnatural proof, and it really is kind of a, I'm showing it to you for the sake of completeness, but you know, I think I owe you this discussion, but what's perhaps more important than the details of my proof is this takeaway message. To change from x to u for a definite integral we must convert integrand from x to u. We must convert the measure dx to du, and we must swap x bounds for corresponding u bounds. In other words, if we're doing a change of variables problem for a definite integral, we have three things we have to. Last time we did 21 examples, and every one of those examples we switched the formulas in x to a formula in u, and we switched from dx to du in such a way that things canceled out, right? Except for that one pesky example that we failed because we couldn't do it. I told you it was impossible. But everything else we saw dx's and du's canceled, right? Well, now I'm telling you, if we also have bounds, we have to switch the bounds as well. Now, let me, unless there's a question, let me give you an example. Yeah? So here's an example. Example 1, integral from 0 to the square root of pi over 2 t cosine of t squared plus pi, right, dt. Now, I wrote over here convert from x to u, but I should mention the x is t in example 1. You know, I mean the original variable to the transform variable more generally. So what I'm going to do here is I'm going to let my u be t squared plus pi. All right, so then du is 2t dt. So t dt is du over 2. All right. So this is integral of cosine of u times du over 2. See, at this point, I've done this one and I've done that one. But I haven't done the third one. I haven't changed the bounds. All right? How do you change the bounds here? So this guy's this is like the f of t in the theorem that I wrote. Okay, and so like in this case, f of a. Well, let me not do that. Let me just go ahead and here's the notation I usually use. U of 0 is what? U of square root of pi over 2 is what? So I'm just saying that this is the f of t from the theorem that I have just erased. If you want to make the explicit connection between what I'm doing in the theorem, think of u equal to f of t. But anyway, what we have to do is we have to evaluate u at the lower bound of 0. So I do 0 squared plus pi, right? So we get pi for 0. So that's why I put a pi right here. Okay? And square root of pi, so I do square root of pi over 2 squared plus pi, right? Which, by the way, is what? That is pi over 2 plus pi. So you got yourself 3 pi over 2. So the upper bound is 3 pi over 2. And what does that give us? Well, we can do the integral now, right? What we got? We got integral of cosine is sine, right? So I've got 1/2 sine of u evaluated from pi to 3 pi over 2. So that's 1/2 sine of 3 pi over 2 minus 1/2 sine of pi. What's the sine of pi? How do you guys think about values for sine? Do you think about the graph? That's how I think about it. See, sine looks like this, you know? So this is pi, this is 2 pi, this is pi over 2, this is 3 pi over 2 for sine theta. Now, of course, you can get out your handy-dandy calculator if you like, but I don't waste time getting my calculator out because I know that sine of 3 pi over 2 is minus 1. So I've got like minus 1/2. And sine of pi is, of course, 0. So the answer is minus 1/2. Questions? No questions yet? All right. Should I do another? Probably should do another, yeah?
Can you just explain again? Here.
Yeah.
Like, almost some stupid thing, but the process when you, from here, like this, what does that mean exactly?
Oh, this is the fundamental theorem of calculus part 2. So going from here to here, I'm using FTC2. Right, so FTC2 said, like, if we have, I'll write it this way, if big G prime of u is equal to little g of u, right, then the integral from, say, a to b of g of u du is equal to big G of u evaluated from a to b. This is just notation. That means g of b minus g of a. So this right here is just what I'm writing is this is FTC2, Fundamental Theorem of Calculus Part 2, in U notation. We wrote it in X notation when we started, but that's what the Fundamental Theorem of Calculus looks like. So, you know, we have an integral, and we have to find an antiderivative and take the difference of the values of the antiderivative at the upper bound and the lower bound of the integral. This is what FTC2 says.
Yeah,
Perfectly reasonable question. I do want you to understand how that step is being made, of course.
Yeah.
Very good. So my next example, here we face the integral from 4 pi squared to 9 pi squared of the sine of the square root of x dx over the square root of x. Oh, can I erase that now?
Yeah.
Okay. Okay, so what should we make u? Let's make u equal to the square root of x, right? Then du will be equal to 1 over 2 square root of x dx, right? Or in other words, 2 du is equal to dx over the square root of x, you know? So great, we see we have a dx over square root of x in the original problem, so that gives us 2 du. And so what we got is we've got integral twice the integral of sine of u du. I just brought the 2 out front just to clean things up. Right now I need to take care of changing the bounds, right? So u of the lower bound, u of 4 pi squared, what's that look like? Well, that's the square root of 4 pi squared, right? And u of 9 pi squared, well, that's the square root of 9 pi squared. How do those work out? Well, that gives you 2 pi, and this gives you 3 pi. So what's going on up here, of course, is all of this thought bubble. All of this thought bubble is just contributing to that. And all of this thought bubble is contributing to this. And of course, the 4 pi squared changes to 2 pi. And the 9 pi squared changes to 3 pi. To put it into words, the 4 pi squared and the 9 pi squared go with x. The 2 pi and the 3 pi go with u. Ah. Man, imagine how many calls I'd get if I actually did get a warranty on my car. I don't know. Let's see here. So now we integrate. What's the antiderivative of sine? Minus cosine. Very good. So we've got minus 2 cosine of u evaluated from 2 pi to 3 pi, right? Which gives us minus 2 cosine of 3 pi minus a minus 2 cosine of 2 pi by FTC2, right? And cosine of 3 pi is minus 1. Cosine of 2 pi is 1. So that gives you 2 plus 2. In other words, the answer is 4. We good?
Yeah.
Okay.
So the area is 4.
The area is 4 under, very good. The area is 4 under the thing I don't want to graph. I mean, What exactly does that thing look like? I don't know. I mean, whatever it looks like. I really don't. It probably looks more like this, from 4 pi squared to 9 pi squared, right? Whatever that thing is. Y equals to sine of the square root of x over the square root of x. This area, like you said, 4.
And for you, are we using the one in the numerator or the one in the denominator?
What?
For you, you got square root of x. Are we using u for the numerator or the denominator? Where do we get
Oh.
u from, basically?
I just guessed it. I wouldn't say it comes from one or the other. The point is, whatever substitution we make, it has to somehow both get rid of the dx and the whatever expression it is, right? And the expression, so in this case, the dx and the square root of x kind of went together to get the du, and the other part was just sine of u, which we know how to integrate. So like, I don't know how to answer that question, like which is the u from this one or that one? I mean, the answer is it's from both. That's the honest answer. It's from both. So I see your question, though. Yeah. And that's a good question, but unfortunately, again, I have to go back to my rather annoying, long, 3-parted answer from last class, which is practice. Know the derivatives of elementary functions, recognize your target is switching the integral to something that we know, an elementary integral that we know, in this case sine. And then if they're bounds, we have the added annoyance of having to change the bounds. Yeah? So let me do a symbolic one here. This is a little bit off the a little bit different, but I think it's a good use of our time. It won't take long. So I've derived kinematics formulas for you before, right? Like if the acceleration is equal to minus g, and a is equal to dv dt, and v is equal to dy dt. I have before derived for you guys that v of t is equal to v naught minus gt, right? And also that y of t is y naught plus v naught t minus 1/2 gt squared. We've derived these before. These are the kinematic formulas, right? These are central to the study of constant acceleration motion in physics. And so if you go, say, from if you had let v of t equal to vf, and y of the final time be yf, right? Then you can solve the above for v, f in terms of v0 with no time. Like you can solve this algebraically. Like you can eliminate time from the second equation by solving for time in the first equation and plugging it in, right? And this gives you the so-called timeless equation. I want to show you how to derive the timeless equation using calculus. So check this out. So we have, A is dv dt, right? But we could rewrite that as dy dt times dv dy. So here I'm using a kind of sneaky trick of multiplying and dividing by dy. All right, so this gives us v dv dy. So v dv dy is equal to a, but a is equal to, in this context, minus g, right? So if I look at this, this gives me v dv is equal to minus g times y, well, dy. And so what the theorem we learned actually says is that when you integrate, so this is a change of variables relation, right? So if you're going to integrate both sides, basically what the logical implication of the theorem we looked at is that if I integrate, this side here from, say, the initial y to the final y, right? Then on the other side, I have to integrate over the corresponding bounds for velocity, which are the initial velocity to the final velocity. Right? Because you have to do a change of variables to get from v to y or from y to v. And so with that, you have to change the bounds appropriately. But how do you integrate v dv? Well, that's 1/2 v squared, right? And I have to evaluate from v naught to vf. And integrate g, well, I got minus gy, evaluated from y0 to yf. And so, hence, I get 1/2 vf squared minus v naught squared is equal to minus g times yf minus y naught, which you could solve for vf squared equals to v naught squared minus 2g yf minus y naught, which perhaps you've seen written as this, vf squared equals v naught squared minus 2g change in y. So this is the sometimes called the timeless equation because it's got no time. Again, you could derive it algebraically by solving the top two equations I wrote, eliminating time, but we just use calculus to derive it directly through a sneaky chain rule argument. This is not on the test. This is just for your information. All right, I'm messing around here at the moment. I wanted to show you kind of a more exotic use of the theorem. So there it is. I have another example. I'll let you guys catch up. Oh, fun fact. If you take this last equation, well, not this one here. So you got, vf squared. So if I divide by 2, 1/2 vf, I'll go back to here actually. 1/2 vf squared plus gyf equals to 1/2 v naught squared plus gy naught, right? Take this equation, multiply it by m, what happens? You get 1/2 m vf squared plus mg vf, give me grief, mgyf equals 1/2 m v naught squared plus mgy naught. Do you guys recognize that? Anybody? This is kinetic energy. This is kinetic energy. And this right here is the gravitational energy, potential gravity. Potential energy due to gravity, mgh. Nobody said physics. Taking it. Ah, well.
We just got into it.
Yeah, so this timeless equation is actually energy conservation in the gravitational setting. It's just kind of hidden.
Like he gave us
So you probably wrote MGH, but here H is Y.
MGL.
Oh, MGL.
The length of the
Oh, height. Uh-huh. But yeah, this is because gravity is a conservative force, so you can look at energy being conserved if you ignore friction and stuff like that. But anyway, let me stop digressing. I'm not probably going to test you guys on that. I mean, I might ask you to derive the kinematic formulas, but it's a calculus question, right? I give you acceleration as a function of time. You integrate it once to get velocity. You integrate it again to get position. That's the problem I'd ask you. I don't think I've ever asked students to derive the formulas I'm currently erasing on a Calculus 1 test. That'd just be mean. Yeah. I might have done that. I don't know. I wouldn't do it to you guys, though. I like you guys. Let's see here. So another example. I think this is example 3. Integral from 0 to 2 pi of e to the sine of x cosine of x dx. So we'll let u equal to, I mean, you kind of got two natural choices here, right? You could either try u equals to cosine, or you could try u equals to sine. If you think about it, if you make u equal to cosine, then there's no way to get rid of the sine, not nicely. So we should try u equals sine, see where that takes us. Well, if u is sine x, then du is cosine x dx, yeah? And so, hey, the integrand is e to the u du. That's nice, but we need to change the bounds, right? And then something kind of funny happens here. U of 0 is what? Sine of 0, also known as 0. U of 2 pi, sine of 2 pi, also known as a 0. So we have the integral from 0 to 0. So we get 0. Well, that was kind of anticlimactic, wasn't it? If you want to make, yeah, I mean, if you want to make this more exciting, change the bound from 2 pi to like pi over 2. You know, if you go from 2 pi to, if we do the integral from 0 to pi over 2, then we get integral from 0 to 1, e to the u du, right? Because u of pi over 2 would be sine of pi over 2, which would be 1. So like there's an alternate version of this problem, which is a little bit more kind of exciting. And so that's what this is. E to the 1 minus e to the 0, right? Which is e minus 1.
Wait, what happens to the cosine there?
I changed the bounds. It never comes back with these problems because we've changed the bounds. So we do the integration in u.
Okay.
There is another way to do the.
Cosine just disappeared.
Yeah, I mean it's wrapped up in the substitution. The thing is, we complete the calculation using u. There is another way to do these problems.
Yeah.
There is another way to do these problems, I should mention. Sometimes, if a problem is very complicated, it's a nice thing to separate the problem of changing the bounds from finding the, the antiderivative. So let me try to think of a complicated problem which will illustrate this method. Well, I need to erase this before, because if it's a complicated problem, it's going to take me the whole board, you know. You guys good? All right. So I will right over here, the other way. Other way. Other method. Number 1, find antiderivative. Number 2, use FTC2 in x variable. So in this scenario, you never change the bounds. Okay. Let me show you how this works on an example that I think warrants it's this technique. So example 4, you might be asked to integrate from 0 to pi, let's say, sine to the 4th of x dx. So how do you integrate sine to the 4th of x, right? So I would say the integral of sine to the 4th power of x dx is equal to the integral of 1/2 1 minus cosine 2x times 1/2 1 minus cosine 2x. You guys remember your trigonometry? So each one of those that I just wrote is what? This is straight up sine squared x, and this is sine squared x. So this is the known identity for sine squared. The tricks we did last class for like sine cubed don't work here, because you don't have like a sine left over or a cosine left over. They go in pairs, and it's annoying. But even powers of sine or cosine require this kind of chicanery to integrate. Now what? Well, now I can multiply it out, right? And so that, you notice there are no bounds. See that? No bounds. I'm just calculating the indefinite integral of sine to the 4th. So I've got 1 minus 2 cosine 2x plus cosine squared of 2x dx, yeah? So reminder, cosine squared theta is 1/2 of 1 plus the cosine of 2 theta, right? In contrast, sine squared theta, which I just used, is 1/2 of 1 minus the cosine of 2 theta. So these you got to know. If you don't know these, you're kind of stuck on these kind of integrals, unfortunately. So what can I do to the cosine squared? Yeah, I can break it up. That's 1/2 of 1 plus the cosine here. So we're letting theta equals to 2x, right? So 2 theta is 4x. Cosine of 4x. Parentheses are your friends, dx. So I'll do one more step before I actually do the integration. So I've got 1/4 integral of 1 plus 1/2 is 3/2 minus 2 cosine of 2x, yeah, plus 1/2 cosine of 4x, right? So there's two different u-substitutions going on here, isn't there? Really, this is a u equals, I make u equals to 2x to take care of this one. I make a w equal to 4x to take care of that one. So like dx is du over 2. Over here, dx is dw over 4. So I end up dividing by 2. I end up dividing by 4 the integral of cosine u, or the integral of cosine w. And anyway, here it is. 1/4. Integral 3/2 is 3x over 2 minus the sine of 2x plus 1/8 the sine of 4x plus a constant. So you should check yourself when you do something like this, right? If I differentiate, do I get back to that? If I differentiate this, do I get back to that? Think about it. Derivative of sine 2x is 2 cosine 2x. The minus stays out front. I got back there. Woohoo. The derivative of sine 4x is 4 cosine 4x by chain rule. And so I got 4 over 8, which is 1/2. We got it. Consider this. If we had used method 1 for changing the bounds, I would have had to change the bounds differently on all 3 pieces. Like the first piece, I didn't make a substitution, so I would have kept the bounds the same. The second piece, I would have changed the bounds with respect to u. The third piece, I would have changed the bounds with respect to w. It would have been a real pain to go through the bound changing here. But now I have it. This is my quote-unquote, well, not quote-unquote, this is an antiderivative, right? So let me just give this thing a name, big F of x, right? And so the integral from 0 to pi of sine to the 4th of x dx is equal to f of pi minus f of 0 by ftc2. That's an antiderivative. Now I can use it. So what happens when you plug in pi into the formula for big F of x? You get 1/4 of 3 pi over 2, right, minus the sine of 2 pi plus 1/8 the sine of 4 pi minus 1/4 3 times 0 over 2 minus the sine of twice 0 plus 1/8 the sine of 4 times 0. I personally didn't need to write all this out. I'm writing it all out for your benefit. I knew from the outset of this calculation that everything I wrote, except for the first term, was irrelevant because it's all 0. Sine of 2 pi is 0, sine of 4 pi is 0, 0 is 0, sine of 0 is 0. 0, 0, 0, 0, all zeros. So the answer here is 3 pi over 8. So in my book, this is the kind of problem that warrants this approach. But you can always use this approach if you just don't like changing bounds. You can find the antiderivative and then come back and apply FTC2 to the original problem. What you can't do is write an integral with du where the bounds are still in terms of x. If you do that, I will take off points because it's a bad habit and it leads to mistakes. Any questions? is good, is no good. It is hard, no doubt. But, you know, you had two choices. So I usually stick with method 1 unless I'm driven to method 2. The other reason to use method 2 is if you've already done the integral. Like if on the test I have like part A is the indefinite integral, and then part B is the same formula but with bounds, then I would use, well, by the previous part, in FTC2, here's the answer, you know. All right, so, oh, okay. So we've done some of the integrals of trig functions, but let's just try to like wrap up that thought. How do we integrate trigonometric functions? Okay, so let's focus on that for a bit. Integrals of trig functions. And we'll throw in hyperbolic trig functions as well, since it's the same, you know, song and dance. So let's take a step back here and do some easier ones. Where was I? Example 5? I can't remember. Am I in, is that right? Okay. So I have already done sine to the 4th, so this is going to be very anticlimactic, given that we've already done sine to the 4th. Well, integral of sine squared, that's the integral of 1/2 of 1 plus, or rather minus, the cosine of 2 theta d theta. Right, and so we can break that up into two integrals. That's like 1/2 the integral of d theta, right, minus 1/2 the integral of cosine of 2 theta d theta. Do I need to write out the u-substitution for that one, or can I just write it down? Can you guys...
Please do the steps.
Do the steps? All right. It's fine. So u equals to 2 theta, du is 2 d theta. So d theta is 1/2 du. So we got, what's the integral of d theta? Well, that's just theta, right? So I have 1/2 theta minus 1/2 of the integral of the cosine of u times du over 2. And what's that give me? That gives me theta over 2 minus 1/4 sine of u plus a constant, right? So you were, so now, so you asked me a question, like what happened to the cosine, right? In this problem, the question is what happened to the 2 theta? Well, we're doing an indefinite integral here, right? So this time, your concern about the 2 theta is justified. It happens. We go back to the u. This is a different kind of problem, right? This is a indefinite integral. Let me write that out. I know it sounds the same when I say it. Indefinite versus definite. Definite is something like integral from 0 to pi, sine squared theta d theta, whatever. The definite integrals are the ones with bounds. The definite integrals are the ones that correspond to signed area. Indefinite integrals, really, it's just finding an antiderivative. These are related, but they are different. They're related through the fundamental theorem of calculus, part 2. So anyway, to wrap up this problem, I've got minus 1/4 sine of 2 theta plus a constant, and there you go. And we just saw how to integrate sine to the 4th in our previous example, right? It was unpleasant, but it's, you know, in some sense just doing this twice, kind of. How would you integrate sine to the sixth? I think the correct answer to that is I won't unless you pay me money. Right? Integrating sine to the sixth by hand is a job. Someone should pay you for that. How about integral of cosine squared? Well, that's the integral of 1/2 of 1 plus cosine of 2 theta. Right? Which gives us, you'll forgive me for skipping steps, theta over 2 plus 1/4 sine of 2 theta plus a constant. The steps I skipped are just like the ones we just did in the previous example, though. So really the only difference is that there's a plus rather than a minus in the original trig identity. Otherwise, it's the same u substitution, it's the same everything. Right? What if we were asked to integrate, like, the integral of Cosh squared x dx? How would you do that? Like, I don't know right offhand. I'd have to think about this one. Cosh of x, remember, by definition, is 1/2 e to the x plus e to the minus x, right? So we can figure out the formula for Cosh squared from that. What is Cosh squared? So I just went ahead and half times a half gave me a quarter, you know, and I'm just writing it like that so we can think about how to multiply it out. What do you get? You get 1/4 e to the 2x plus e to the minus 2x plus 1 plus 1. See, e to the x times e to the minus x is equal to 1 is the thing I'm using, yeah? Those are reciprocal. So, oh, hey, look at that. That gives me 1/2 of 1 plus 1/2 e to the 2x plus e to the minus 2x. Oh, that's kind of funny. So apparently Cosh squared x is also equal to 1/2 of 1 plus the Cosh of 2x. So there's a similar identity for hyperbolic cosine squared as there is for cosine squared. But I'd like to point out, you don't have to do that. Did you guys see that? Like, if you're just after integrating Cosh squared, we could have just as well stopped where? Like, I would point out, do you guys agree with me? If we just look right